All right, welcome back. And today we're going to look at two things. We're going to look at hot water heater calculations. How long does it take to heat up between two different temperatures? And the other one we're going to look at is we're going to derive a differential equation from the first law of thermodynamics to solve for temperature as a function of time of a hot water heater when the power goes out. Okay. And then your job is to create an Excel or an Octave code, a programming code. It could be Python, C, whatever, that calculates these. All right. So you're going to create a programming code. So let's first do this one. So, how long, if we have a hot water heater, how long is it going to heat up? Or how long does it take to heat up to temperature, to a certain temperature? So, let's go ahead. I'll make this bigger. Given. Zoom in a little bit more. We have a 20-gallon hot water heater. T1 is going to be 25 degrees C. T2 is going to be 50 degrees C. And the electric power of this hot water heater is 4.5 kilowatts. Okay, so we got a 20-gallon tank. It starts off at 25 degrees C. We're going to heat it up to 50. We have electric power of 4.5 kilowatts. How long is this hot water heater going to take to heat up? All right, so here's our electric power in. Q could come out. Here is our boundary. This is a closed system. Okay, we don't have any flow in or out right now. All right, even though they're in a hot water heater, you do have, but this, we shut the valve off. There's no running water. It's closed. Okay, so we're just heating the hot water heater. We got properties of water. Density is 1,000 kilograms per meter cubed. Some assumptions. We got steady state, no flow. We're going to assume adiabatic, so there's no heat transfer out, so it's well insulated. And we're going to neglect any elevation changes. Okay, so don't worry about any of that. It's not, this hot water heater system is not moving in space. So the system only has temperature changes within. Okay, so we're going to find T, the time it takes to heat up. All right, let's get to the solution. So first law, closed system. So all we have is delta U over delta T is Q dot N plus W dot N. Okay, so on the left of the equal sign is our system. So this hot water system could be moving with some speed, so kinetic. It could be changing elevation, and it could change temperature, which is delta U, okay, internal energy. However, it's stationary, so no potential, no kinetic, but only temperature. And on the right side of this, these are energies that's crossing the boundary, okay, which is the dotted in my sketch. And we actually are assuming that this is 0 and we only have electric power going in. Okay, so we got delta U equals W dot E times delta T. I just multiplied it over. Okay, Why? Because I want to solve for delta T. Delta T is equal to delta U over W dot E, our electric power in. We can rewrite delta U as the mass times U2 minus U1 over the power in. All right. U2 and U1, that's the internal energy of the water at a temperature, and you can find that in a table. Okay. So delta T equals the volume times the density, which is mass. Okay. That's mass times U2 minus U1 over the power. All right, and then you can find U1 at T1, which is equal to 105 kilojoules per kilogram K. U2 at T2 is 209 kilojoules per kilogram K. And this is found on table A4, and I'm going to show you that right now. So if I go here, I go to my table, and what we have is what? 25 degrees C, so here on the left is 25. So I'm just going to go over here and draw this whole line here. And the other one is 50. And let me do red. So U is internal energy, and we're going to look for the subscript F, which is the fluid, okay? Boom, right there, 105, I rounded, and then at 50, it's 209. Okay, so remember, F is the saturated liquid, and we can use that for water, okay? Where G is the saturated vapor, that's on the right side of the vapor dome, that's a gas, okay? So liquid, we're looking at liquid, so UF. So we can find these values, can plug them back in. We have the volume, 20 gallons, convert that to meters cubed. We have the density. We have U2, U1 in kilojoules. Make sure you do those in joules. In watts is in, or sorry, power in electric is in kilowatts. To convert that to watts. So use this equation and create a programming code that will calculate this. Okay? Be cool to find, so do two. I want to also know T1 at 10 degrees C and T2 at 50 degrees C. Okay? So this will help you. This is kind of a quick derivation on how you would find the time it takes to heat up a hot water heater. Cool. Now, let's look at finding an equation, which is called a differential equation, for the time it takes to cool down a hot water heater when you have no power and you turn on the water at different flow rates. Okay? So, given, very similar, volume, 20 gallons. We're going to say the mass flow rate, 2 gallons per minute. The tank is at 52 degrees C. And the water coming in is at 4.44 degrees C. And we're going to stop at 40 degrees C because if you go anything below that, you could actually have bacteria start growing. So 40 degrees C is a good temperature to eliminate any issues with water. Okay? You can safely use that. We got density of water, 1,000 kilograms per meter cubed. And we have this specific heat value of 4,200 joules per kilogram K. We're gonna need that in a little bit. So let's look at the sketch. Here is the hot water heater, and this time I'm going to put flow in. And let me do green again for the boundary. Okay. And let's look at, we got heat out. We could also have electric in. WE. And then we could have, we got fluid energy in, which I'll call E1. And this is dot. We could have energy of fluid out, which I'll call E2. And that's good for the sketch. Properties, or no, sorry, assumptions. Steady state. The diameters of the pipes in and out are the same. So we don't have to worry about change in velocities. It's adiabatic. So Q is 0. And we're going to assume that the power's out. So there's no electric in. And we're going to find basically a differential equation that you can then, that I want you to solve numerically to find the temperature as a function of time. Okay? Cool. Solution. First law. This is of an open system now. So we're going to, I'll write the whole, I'll be complete. So this is the left of the equal sign. This is the system. Okay. And then here is everything going through the boundary. So you have heat, work, and then energy of the fluid. So this is energy in. And then you subtract energy out. Okay. So again, let's look at the left of the equal sign. That's gone and that's gone because this hot water system is not moving in space. It's stationary. So only the temperature of the water changes inside of the system. Okay. On the right, it's adiabatic. So there's no heat loss through the boundary. It's well insulated. Okay. There's no power. There's no mechanical work. So that's gone. These, I'll put up at the top. This is energy of the fluid in, and this is energy of the fluid out. In the energy of the fluid, okay, you could have kinetic, which is this one. You could have potential, and you can have what they call enthalpy, which is actually, I'll put up here, internal energy plus pressure energy. So internal energy, U, relates to temperature. So something will have energy based on its temperature. And then this is pressure energy. Think of it as like an air compressor. You pressurize the air. It now has stored energy. And when you open the valve, that energy then is released to kinetic. Okay? So you can kind of think of a squirt gun the same way, right? However, we can cancel some stuff. The pipes are the same, so the velocity in and out are the same. We're neglecting any elevation changes, which we'll put here. No elevation changes. We're going to neglect those, okay? They're small. So we only have enthalpy and internal energy. So let me rewrite this. Delta U over delta T is m dot 1 H1 minus m dot 2 H2. Now the mass flow rates in and out are the same. Okay, so if we did conservation of mass, that states mass flow rate in must equal mass flow rate out. So m dot 1 equals m dot 2, and we're going to call this just m dot. So we're going to combine those. We got m dot h1 minus h2. Cool. All right. Let's just kind of keep plugging some stuff in. I'm going to rewrite the big U, okay, as mc delta little u, or sorry, nope, delta t, okay, because that's a governed equation, okay, where u equals mct, okay. That's just a fundamental equation that you'll learn in thermodynamics, okay? Where this C is that value I wrote above. It's like a constant, okay? And then I put the delta in there because it's delta U. And then over delta T equals m dot, and I'm going to write enthalpy out. So U1 plus P1 over rho minus U2 and minus P2 over rho. Okay. I'm going to cancel the pressures because they're the same. Okay, we're not pressurizing anything. And so what we have is mc delta T over delta T, m dot U1 minus U2. Okay, so the pressure at 1 and 2 are the same. That's what we're assuming. We're just saying that the temperature difference between coming in and going out are going to be different because the water coming in is at what? 4.4. So T1 is 4.4 degrees C. This temperature right here is changing, and therefore this temperature out is also changing. Okay? The tank temperature starts at 52, and then it heats up. Okay, sorry, it doesn't heat up. It cools down because the power's out. All right. So eventually what's going to happen is this temperature is going to get to 40 degrees. Okay, and we're assuming that pretty much the temperature inside here is also T2. Okay, that's another assumption that we're assuming. Okay, so the temperature going out is the same as the tank. Okay, so the tank temperature starts at 52. We have 4.4 degrees C coming in. It's going to cool the temperature down to a point where it's not safe anymore. Okay, and that's what we're trying to find. All right, cool. So I'm going to keep... did I miss anything yet? No. Okay, I'm going to also put in that U equals C times T, because remember, big U is mct. So mc delta T over delta T is m dot. This would be C T1 minus T2. Okay. And then we can cancel the C's. And then we end up getting this. And I'll rewrite it like this. M dot over M, T1 minus T2. So we now have developed what they call a differential equation that relates temperature as a function of time. It has mass flow rate. It has the mass of the tank, the temperatures of the tank, and the water coming in. Okay. So use this equation and solve for the time of the water in the tank. So we have temperature, time, and you should get something like this, okay? Where this is 52 degrees, and this will eventually be, you can say 40 degrees C, okay? Okay, so just to recap this problem, go back up here. We have a hot water tank, and we have, let's do this. We have no power, so basically the electric is off. We have no heat transfer because it's adiabatic. We're assuming it's well insulated. So we have water coming in at 4.4 degrees C. We have the temperature of the tank, and then this is T2. Now, I'm also going to assume that this is the temperature of the tank. Okay? So the temperature of the tank starts at 52. It's going to cool down because you have 4.4 degrees. And therefore, we're going to reach at some time an unsafe condition of 40 degrees, okay, or below that. All right. So we will get a graph that's like this, okay? Starts at 52 and drops. So what we did, go over here, we used the first law, and we neglected kinetic potential of the system, okay? And just a side note, you use these two in physics class with a ball, okay? And you neglect this one because the ball doesn't change temperature. But in thermo, temperature changes, so you use this pretty much most of the time. Again, left of the equal sign is the system. Right of the equal sign is energy in and out of the boundaries. It's adiabatic, no power. Then we have flow coming in and flow going out. Okay, so we canceled a bunch of things. We used conservation of mass. We also plugged in some other known equations for U. And what we ended up having was this boxed equation that solves for temperature of the tank with respect to time is mass flow rate over m, T1 minus T2. Okay, so I'm going to assume that this is the tank over dt, m dot over m. This is T1, so it's always going to be 4.44 degrees C minus T of the tank because we're assuming that whatever goes out is the temperature of the tank. Makes life easier. Okay, and we can include that in the assumptions. T of the tank is close enough to T2. Okay. So use this one, okay, and use a numerical method. So program it so it solves for the temperature of the tank as a function of time to get a graph that should look like this. Okay, best of luck, and let me know if you have questions.